Expand and continue finding roots of polynomials. The big difference is that now we're going to look for real and complex roots. Now, one thing that's true about all polynomials is that the degree tells you how many solutions you should get or could get. Now, in this case, I've got a degree 3 polynomial. I could get as many as 3 solutions. Now, I'll get exactly 3 solutions if you count multiplicities and complex numbers. Let's see what happens here. When I'm looking for the roots, I'm looking for the graph crosses the x-axis. I only see one. Does that look like a bounce, wiggle, or straight through?
Wiggle.
Wiggle.
It looks a little like a wiggle, but let's see if it really is. If I want to find where these roots are, I could set p of x equal to 0. That would mean x cubed plus x equals 0. So, okay. Now, if I'm stuck solving this, I'd probably factor out the x, which is behind x squared plus 1. And, okay, well, I've got 2 possibilities here. Because I've got something times something else equals 0. So one of these things has to be 0. Either x is 0, well, I kind of knew that. I could see that one without any problem. Or x squared plus 1 is 0. Now, where is that true? Well, that means x squared plus 1 equals 0, or x squared equals negative 1. What could x equal? What's the square root of negative 1?
1 plus or minus 1.
Try again. Square root of negative 1 is I. Oh. So let's take a look at our polynomial. We can write this as a completely factored polynomial now. Remember, you got the roots and you got the, well, you know what the multiplicity is for each of these. So I got roots at x equals 0, x equal I, x equal negative I. The corresponding factors are going to be an x, x minus I, and x plus I. So writing this factored, p of x is going to be x times x minus I times x plus I. But how many real roots did we get out of this? How many of these roots are real? 1. So this is false. If false, give a reason. There's only one real root. And that's x equals 0. That's the only real root. These are complex, or often called imaginary roots. So only one real root. And we're done. We're done with that one. Yay. Let's move down to the next one. So Johan, if I wanted to find the roots of this polynomial, what would you suggest we do?
Break it down.
How?
Let's see. But just see. I would just give.
So roots is another way of saying that is zeros. You're going to set x squared or x to the 4th plus 9x squared equal to 0. And break it down might be interpreted as factoring. So I'll factor out the x squared here. So it leaves behind x squared plus 9 equals 0. Now I can see where the first term would equal 0, right? Where does x squared equal 0? Well, at 0. So we expect it to be 0 there. How about this part? Where does x squared plus 9 equal 0?
Plus or minus 3.
So good, x squared equals negative 9, x equals plus or minus square root of negative 9, which is plus or minus 3i. So I've got 2 roots here, and I've got 2 roots here. So let me rewrite p of x as x squared, and then x minus 3i and x plus 3i. Great. There it is, completely factored, and I've got all my roots. So I've got roots at 0, 3i, and negative 3i. Am I going to see those roots at 3i and negative 3i when I look at the graph?
No.
No. Is there anything I can see about my graph that, you know, I could relate to? Think about what happens here at x squared at x equals 0. Is there a feature of the graph that I should see when I look at this graph?
Bounds.
Yeah, I should see a bounce at 0. So let's see, 3.5. I thought I had one for 3.5. Let me just take a look here. No, there it is. So it's for 3.5. Yeah, we got a nice bounce here at 0. All right, so we can feel a little bit reassured by that. But there's your roots, there's your factor completely. Now, here's where I get mean. Here's where it gets more challenging.
Oh, boy.
So let's take a look at example C, and I'm going to pull out a fresh sheet of paper for example C. Example C. I'm not going to try and squeeze it in a little space here. We want to do the same thing here that we did with our previous problems. I want to set p of x equal to 0 and solve. So if I set that equal to 0 and solve, then what's a good first step?
Factor out an x.
Yeah, absolutely. Factor out an x. That's x times x squared minus 4x minus 20 still equals 0. Well, one of these is pretty easy to see, right? Clearly, x equals 0 is a solution, but now I also got to deal with x squared minus 4x minus 20. I'll give you a minute with that one. Did I got the signs right on this?
No, plus 20.
Thank you. That should be a plus, plus, plus. All right. That'll make it more challenging. So at this point, you should be convincing yourself of something, that it doesn't factor.
Does that affect?
Yeah, you look at that and go, yeah, there's no two numbers that multiply to 20 and add to negative 4. So, all right, that means the quadratic formula, A, B, and C.
Plus or minus square.
So I'd have a 1.
C over 2A.
Yeah, exactly. A 1, a negative 4, and a positive 20. Let's see here. 4, there we go, 20. Thank you, Oz. So let's fill things in. Negative of something plus or minus the square root of something squared. That would be our B. 4AC over 2A. Now, in the interest of time, I'm just going to fill these things in for you. I hope that you're comfortable with the Pythagorean or the quadratic formula. The reason I put the parentheses in here first is especially for problems like B, or like this one with a negative value of B. Because it's very easy to miss that double negative, the negative of negative 4. Or when you square things, there's a tendency to give me negative 16 instead of the positive 16 that it should be. Now there's some more tendencies as well. Let me talk about those as we go through it. I've got a 1 here and a 1 here. And finally, a 20 here. So 4 plus or minus the square root of 16 minus 80 over 2. And here's another place where I see some perhaps wishful thinking or, I don't know, something else. What's wrong here?
Negative out of the 64.
Yeah, it's wishful thinking, but this is a negative 64. Good job, Nick. Thank you. Ryan, what's the square root of negative 64 going to be? Ryan,
Plus minus 8i.
nice. So you're going to get 4 plus or minus 8i over 2. Now there's a couple ways you can handle this. I like factoring out, like a 2 and then canceling. But another way is you could just do 4 over 2 plus or minus 8i over 2. And separating these into two factors is kind of nice. A lot of times if you have a complex number as an answer, that's the way WebAssign wants it, with a positive solution and a negative solution, or an A and a BI. So if you see, A plus or minus BI, then it wants separate terms for A and BI. It doesn't want things like this. I'll accept stuff like this as long as it's in lowest terms, but WebAssign gets a little picky. So if you try to give it that, it's going to balk. It wants it like that. Okay. I've got my roots now. Let's put this back together in terms of some factorization. So make a little table for ourselves, roots, and then corresponding factors. So the roots started out with an x equals 0, and then an x equal 2 plus 4i, and x equal 2 minus 4i. The factors that correspond to this would be an x here. How about this one here? X.
Minus 2 plus 4.
Actually, both of them have to change sign. So the way to get these factors is you move these terms to the other side. So when they change signs, they change sides, they change signs. Try it again with this one.
Minus 2 plus 4.
Thank you. Minus 2 and plus 4i. So overall, your polynomial could look like this. P of x equals x times x minus 2 minus 4i and x minus 2 plus 4i. So,
That's the last answer.
yeah, that's it. That's completely factoring our polynomial p.
See that's a lot easier than the one where you had a root left in it and I.
Yeah, I know. Maybe I'll have a good weekend. Maybe I'll, win the squares on my Super Bowl game or something like that, and I'll be generous. But let's see what some of the other things that you can run into would be. So, for instance, example D is another example, and sometimes when I choose these things, I try and choose problems that set you up for the homework. And this one in particular is one that we got to work on with respect to the homework. So what's going on with this? If you take a look at this, this might remind you of something that we did in intermediate algebra. And we had things that were quadratic in form. Let me just look for a minute. Instead of looking at this, let me look at u squared minus 7u minus 8. All right, that looks a little bit more user-friendly than this. Can anyone factor this for me? U squared minus 7u minus 8. Let's just ignore the original problem for a moment. Nick?
U minus 8 and u plus 1.
All right, u minus 8 and u plus 1. Perfect. So we got it factored. That's nice. Well, how did I get that, out of this? I made kind of a little substitution. U is equal to x cubed. And then u squared would automatically be x to the 6th. So these two are the same. And if I go back now and I substitute back in for x cubed, I get x cubed plus 1 and x cubed minus 8. So that's what I'll get if I make my substitution back. It's just kind of a clever way of figuring out how to factor this. You don't have to do it this way. I'm just mentioning it because it does help some people. But here's going to be the real challenge for you right down here, is remembering how to factor this guy. So that's going to be your sum of cubes, and this is going to be your difference of cubes formula. And I know those are on the tip of your tongue, but let me just remind you what they factor like nonetheless. A cubed minus B cubed is going to be a binomial times a trinomial. A cubed plus B cubed is going to be similar. In fact, at this point, they're very similar. Let's say identical. The only difference is that they have different signs that go between them. Does anyone remember what that SOAP acronym is all about?
Same, opposite,
Same, opposite.
always the
Always positive. There you go. All right. Same, opposite, always positive. So that would be a minus. That would be opposite. So that's a plus. And that one's always positive. Do the same thing for yourself down here. Try and race me. Fill in those signs. Same sign, opposite sign, always positive. Now, when you factor a trinomial using this formula, you're going to get a binomial times, when you factor a binomial using this formula, you're going to get a binomial times a trinomial. This trinomial is always going to have complex roots. So I'll tell you that right now. We'll have complex roots. This part should be pretty easy. That's just going to be a linear factor, won't be a problem. But this one, that one's going to be a pain. So let's see if we can't finish factoring this. This is going to factor as a binomial times a trinomial. So that's this part right here. What you should do is ask yourself, what do I cube to get x cubed? Oh, that would be an x. What do you cube to get 1? That would be a 1. And then you're going to take this term times itself, x times x. That gives you your first term. I'll take this term times itself. That gives me my last term. And then this term times this term, x times 1. That gives me my middle term. I need to throw in some signs here.
So it's minus, plus, always positive.
Same sign, opposite sign, always positive. Perfect. Now test yourself on this other one here. So this other one, let me do this. Again, you're going to have a binomial times a trinomial. So ask yourself, what do you cube to get the first term? Well, that'd be an x. What do you cube to get the second term? 2. And now take these terms, don't worry about the signs until you're all done. Take these terms and figure out what goes in between. It's going to be x times x. That'll be an x squared. 2 times 2 is a 4. What term am I going to put in between these things?
2x.
Yeah, x times 2, or better yet, 2x. Mina, what signs go in between here, please?
Minus.
Same sign, good, minus.
Positive.
Opposite sign is positive,
Positive.
always positive. Great. So, a lot of work to get this factorization. You probably will see a difference or sum of cubes someplace in your homework. I haven't written the exam yet to know whether or not I actually want to do that to you in terms of a problem. Mostly because out of pity, because I know that the difference in sum of cubes factorization isn't very nice. And, you know, unless you practice it a lot, you're gonna forget it. We got a lot of work in front of us to finish solving. Can you see what we have to do to finish solving? I gotta set this equal to 0. This is our P of X. It's as factored as we can get it. What do I have to do to finish solving?
You have to factor that again.
That's a great question.
This, you can't-
These won't factor. Those trinomials will not factor. So if they won't factor, what's our alternative?
Why will they not factor?
They just don't. This part's always gonna be a quadratic. You're only gonna get one real solution out of these things. Yeah. You can kind of convince yourself of that if you look at the graph of x cubed minus something and x cubed plus something. So let's just kind of take a quick look at something like that. If I did y equals x cubed, I don't know, give me a nice easy cubed number, like 8. X cubed minus 8. Well, that graph only crosses the x-axis once, right? So it only has one real root. If I made that a plus 8, well, I still only have one root. Or plus 27, you know, again, the same thing. You're only gonna have one root. That means the other two roots have to be complex. We'll talk about that in a second. I don't really think I want to take 10 minutes to go through all the calculations here. What's going to happen here, and I'll put this in the notes, is that when you solve this, we can see two of these solutions, right? Where are two of our solutions? X equal what? If I set this equal to 0, what would be one of the values of x that can make that equal to 0? -1 and 2. Now the rest of this is going to come from setting each of these trinomials, these quadratic equations, equal to 0. Kyle, what do you think we're going to have to do to set each of those equal to 0 and solve?
Factor.
All right, probably not going to factor because they're going to have complex roots. Angel?
Yeah, we still find values because we wouldn't affect it.
Yeah. So each of these you're going to have to set equal to 0 with the quadratic formula. So
Are you writing something down?
no, I already had this written down. I'll put this in the notes. But you're going to take that term and set it equal to 0. Oops, excuse me. I'm sorry. All right, now I see what you're saying. My bad.
Okay.
So you're going to take this term, set it equal to 0 with the quadratic formula. And it's just a pain. And then you're going to set this one equal to 0 with the quadratic formula. And you'll get two solutions. You'll get, well, you get a total of 4 solutions. You'll get this one from our first quadratic equation, and this one from our second quadratic equation. It's a pain. There's just no two ways about it. Like I said, I will put this in the notes. Let me zoom out a little bit so that you can kind of see all the work here. But it's just a pain. There's not much you can do about it. Just grin and bear it. Do keep in mind that I am reasonable on exams. I'm not going to put this problem in particular on the exam because it's just too long. I'm not that mean. All right, there's a couple other little problems that we got to knock out while we're here. And that would be, let's see. Let's take a look at example F, and then maybe example G. So for example F, what you might have noticed in working with our polynomials is that we always end up with certain pairs of complex solutions. And that goes back to your root finder's toolbox. You can have what's called the imaginary zeros theorem. And that is if you have a polynomial with real coefficients and you get a plus bi as a root, then a minus bi is also a root. They occur in pairs. So if you look back at our last example, we had 1/2 plus the square root of 3 over 2i. Then we also got 1/2 minus the square root of 3 over 2i. They occur in pairs. -1 plus I times the square root of 3, -1 minus I times the square root of 3. So they occur in those special pairs. Now what does that mean for us in terms of solving these kinds of problems? Well, they tell us we have a polynomial with real coefficients that satisfies the following conditions. We've got a degree of 3 and zeros at x equal 3 and x equal 2i. So let me write the roots and then the corresponding factors. I've got a root at 3, so that's going to be x equal 3. What's the corresponding factor?
X minus 3.
X minus 3.
X minus 3. I've got a root at 2i. What's the corresponding factor?
X minus 2i.
X minus 2i. And that's all they tell me, but there's something else that's implied. If x equals 2i as a root, then x equals negative 2i is also a root. And that's something that you get from the imaginary zeros theorem. So this one must also be a root. And the point of a problem like this is for you to realize that that has to be a root. And if that's a root, Annie, what would be the corresponding factor there?
X plus 2.
Perfect, x plus 2i. Now when they ask you for q of x, that is this polynomial, thank you, Annie, we're going to multiply these together. X minus 3 times x minus 2i times x plus 2i. And let me make a suggestion for you when you multiply these together. Start with the complex terms first. So I'm going to start with those two right there. And we'll leave the x minus 3 till when we're done. What happens in here? Well, it's just an application of FOIL, right? First terms, outside, inside, and last. But something special happens on the inside. Does anyone know what that is?
They cancel.
Those cancel. What happens to minus 4i squared?
It becomes a positive 4.
Becomes a positive 4. So x minus 3 times x squared plus 4. And now it's just a matter of distributing. I'm not going to use FOIL in the exact order, but it still will get me to the right place. I'll get an x cubed minus 3x squared plus 4x minus 12. And that is your final answer. Now you're in luck. I get to do one more like that, except a little bit harder. So before we do the harder one, are we okay with that one?
Yeah.
Example G. Have a thumbs up? Doing okay there?
I'm just.
All right. Yeah, just, I understand. This one's a little bit more generous in that Q has a degree 2. So that's something nice to notice. Q has degree 2. All right, good. And it's got a root at 1 plus I times the square root of 2. All right, so let's see. Let's see. How do I get this? Example G. root x equals 1 plus I times the square root of 2. What's the corresponding factor?
X
X minus
X minus 1
minus
I squared.
minus I times the square root of 2. Now, if this is a root, what else has to be a root?
X equals minus.
Minus I.
Thank you. All you're going to do is change the sign on the complex part of your term. Don't change the real coefficient. So we've got the first one is a root that was given. And it corresponded to this as a factor. What's the second one going to look like?
X minus 1 plus I root 2.
Nice. Now, as far as determining Q of X is concerned, let me give you a reminder. This is kind of a nice little trick if you can use it. If I multiply A minus B times A plus B, if you foiled this all out, you'd see that the middle terms cancel. And you're just left with A squared plus B squared. Well, how is that relevant to what I have here? Let me show you. So Q of X is going to be X minus 1 minus I times the square root of 2 and X minus 1 plus I times the square root of 2. So far, it doesn't look too much like what I have up above. But let me work on that with you a little bit. Let's put parentheses around that x minus 1 term and regard it as one whole term. Is this starting to look a little bit like this formula up here? What would my A be? A be the x minus 1. What's B? Oh, it's I times the square root of 2. So if you can piece it together like that, you can save yourself a lot of work. Now, there's nothing wrong with multiplying it out all the way. You'd have 9 multiplications to make. You'd have to distribute the x times all these terms, and then the negative 1 times these terms, and then the negative I squared to 2 times these terms, and then you got to combine like terms. You could do it that way, but man, I wouldn't.
Where's your,
This-
just I?
This is your A, so I'm going to have x minus 1 squared minus something else squared. What's my B in this?
The I just squared.
I times the square root of 2. So that looks a lot easier, right, to start with. Now, I've made mention of this trick before. It's helpful if you can square out x minus 1 in binomials like this in your head. You're going to get the n term squared, x squared, and negative 1 squared is 1. And then the middle term, I borrow this 2 up here. 2 times x times negative 1 gives me negative 2x. So that's that. What do I get when I square I?
I squared.
I squared is
Negative 1.
negative 1. What do I get when I square the square root of 2? 2. So you have 1 minus negative 2, x squared minus 2x plus 3. That's going to be your final answer. So, whew, wow. Give yourself a pat on the back if you're still here. That's awesome. Did that last little bit go too fast? Is that okay there? That's a really good trick. It saves you a lot of time on doing those things. All right, let's call it a day and